everybody, welcome back to Measure Theoretic Probability. In the last video, we were beginning to talk about random variables. And a random variable is a function that takes an outcome from an experiment involving randomness or probability and produces a real number. For example, if you flip a coin, fair or otherwise, you might define a random variable x to be 1 if the result is heads and 0 if the result is tails. So more generally, we're going to have a non-empty set omega and a whole probability space. So we're going to have a sigma field curly f and a probability measure p on omega. And maybe let's envision omega looking like this. And then x is going to be a mapping, and that's going to take us to the real line. So I'm going to draw my reals not looking like a line, simply because I'd like to be able to draw a kind of weird generic set without having to chop up a bunch of intervals and single points. And, this is an easier way for me to say, here is a set in R that could look really weird and discontiguous and all of that, or not. So my question to you is, what is the probability that this random variable results in a point that's in this set A? So I've written PROB, prob, the probability that X is in A. This is what we want to find. I didn't use the letter P because that is a specific function that is a measure over here on this space. But this space is where the randomness happens. So if you want to know the probability that X takes its values over here, you need to figure out what values those correspond to back here. So suppose these are the sets that correspond to the values under the mapping X that end up in this set. And these are the sets, and these are all the sets. I can now answer this question based on measuring the sets back here so my probability is going to be the probability measure of these sets back here if that set is measurable. And that means that it has to be in curly F. Because those are the measurable sets for which we have defined the function P. So this is the nice property. If you want to be able to answer probability questions over here, you need to convert them back to probability questions over here. And if your measure is not defined on this set that you pulled back, then you have a problem and you don't have a valid random variable. This purple or pink or whatever color you're seeing or not seeing over here are all the points that map into this set A under the function X. And we can write this as the set of little omegas, and if you want to be more complete, little omegas in capital Omega, such that X of little omega falls in A. We're going to be writing sets like this a lot, so it's nice to have a more compact notation. We're going to write X inverse of A. And this does not mean the function is invertible. If there's a set in here and you're looking at an inverse on a function, this means the inverse image of this set under this function. It means precisely this line above. So we're ready to define a general random variable. Last time we only talked about simple random variables, and this time as well, but I'm going to slip this definition in now. Suppose we have a probability space consisting of a non-empty set omega, a sigma field curly f, and a probability measure p. I want to pull back sets from R and make sure those pullbacks, those inverse images, are in F. That is going to be the nice property again, but we actually don't need to pull back every set in R. We have a sigma field in the omega part. We also can have a sigma field in the R part. And our most common sigma field used there, the most natural sigma field, you'll recall, is the set of Borel sets that I'm denoting with a curly B, sometimes written curly B of R. You'll recall that these are all the sets that can be generated by open intervals of the form open A to open B, and we did a lot of manipulations and saw that we could get closed intervals, half open, half closed singleton points, and other much weirder things. Something that people always ask at this point is there any subset of R that is not a Borel set? And the answer is yes. I really don't want to divert, but let me just quickly say a lot of people think it is the Cantor set, which is a set where you take the unit interval from 0 to 1 closed, and you take out the middle third, and then you take the remaining parts, and you take out the middle third of those, and then you take the remaining part and take out the middle third of those, and it creates a really funky set. That's actually a Borel set, but the Cantor set is something off of which you can base a non-Borel set. So you can put it through something known as a Cantor function as an example of a non-Borel set. So bottom line to that aside is the Cantor set actually is a Borel set when people usually quote it as an example of not a Borel set. But I totally digress. So let's get back to the definition. We have a probability space. We have a space R with a Borel sigma field on it, and a function x from omega into R is a random variable if the set of omegas for which x of omega falls into a set B pulls back into a set in the sigma field F for any set B in the Borel sets. So a definition actually depends on the sigma field we used in R as well. We use the Borel sets because that is by far the most common sigma field that people use in R, but we could define a different sigma field in R, in which case we would say something like X is measurable F/F2, where F2 was another sigma field, something like that. But we're not going to have to worry about that for a while, so we'll get there and I'll say that all again. But yes, you are correct that measurable with respect to F is actually also a product of what sigma field was used on R. We just don't write anything like that right in here because the Borel sets are assumed to be the sigma field. So just to use our shiny new notation, we're saying here the inverse image of any Borel set B falls in curly F, the sigma field on the omega set. So last time we were talking about simple random variables, and these are random variables that take on a finite number of discrete values and also have this other property. We had a definition with property I and property double I, and I will be putting that back up again in a few moments if you don't remember it. But it doesn't say anything about Borel sets. And right now, I want to convince you that if we pull back and look at the inverse image of Borel sets for a simple random variable, we'll get the same thing as if we just look at pulling back individual points. In which case, we don't have to consider all Borel sets. It's much easier to check whether or not a simple random variable as a function is measurable. It is enough to pull back each distinct value over here. Now, the definition says we have to pull back Borel sets. So let's take a Borel set B. One way that could fall over here is that it might contain none of these 4 points. And that means that nothing maps to it because the function x does take everything in omega somewhere. It doesn't put it all onto the reals. In this case, we're only going to 4 values, but it does take everything from omega. Everything from here maps to one of these 4 points, so nothing lands in here, and that means the inverse image of this set is the empty set. And the empty set is in whatever sigma field we put on the space over here. So here is an image of everything in omega going somewhere. They don't have to look like contiguous regions like this, but these 4 colors over here are representing the points that match to each of these 4 points over here. Let's lock down these points. I have chosen 4 points, so a simple random variable takes on a finite number of discrete values, and just for this example, 4 points. Let's call them little a1 through little a4. Those are real numbers. And let's go back to checking measurability of this function. According to the definition we had today, we have to pull back Borel sets, and so far we've pulled back one Borel set, which did not contain any of these points over here. But suppose we have a Borel set in R that contains exactly one of these points here. So you have to ask yourself, what points in omega mapped here? The points in omega that map into this set are precisely the points in omega that map to this single point right here. In other words, the inverse image of this Borel set under X is the same thing as the inverse image of this point. F is the same thing as finding all of the omegas over here that map to this one point. So this is me trying to build up why I said that you really can just look at pulling back the single points and not have to look at all Borel sets. I think you get where I'm going with this, but let's take one more. Suppose I take a Borel set in R and it looks like this over in R, containing exactly 2 of the outcomes for our random variable. Then if you pull back to where this came from, we have a group of points over here that map to this point and a group of points to this point. So we pull back to a group kind of like this, which can be written as the union of the points that map here and the points that map here. In other words, the inverse image of a Borel set that contains exactly 2 of these values can be written as a union of 2 of these inverse image sets of single points. And again, that's what I was trying to convince you of. For a simple random variable, it suffices for you to look at single points. Because if this inverse image is in the sigma field over here, and this inverse image is in the sigma field over here, then the union is in the sigma field because it's a sigma field. And then at least checking this part, that x is appearing to be measurable. So I didn't actually show that x was a measurable function here, because we do need these pullback sets that I have denoted with these 4 colors to be in the sigma field. And maybe they are, maybe they aren't. I haven't really told you what the sigma field looks like. But hopefully I have convinced you that instead of pulling back Borel sets, if you have a simple random variable, it's okay to just pull back and look at the inverse image of single points. Okay, so let's go back to our formal definition for a simple random variable. We've got a probability space, an omega, f, and a p, and we have a function x taking points in omega into R. We say that it's a simple random variable if, number 1, it takes on finitely many values, like the 4 in the last example. And number 2, we had that for every x in R, the set of omegas for which omega maps to little x under the function x needs to be an f. So all those pullback sets need to be measurable. And then this is now what we know to be the definition of the function x being a measurable function. We are looking at the inverse image of all Borel sets without having to talk about Borel sets. In the last video, we looked at an example of a random variable, a simple random variable made from a sum of indicators. So suppose we have a random variable that looks like this. I've got a sum as I goes from 1 to k of a little ai, where these little ai's are real numbers, and then an indicator that says omega is in some set, capital AI. So if I plug in a little omega from the omega set, it's going to fall into, so we've got subsets, capital A1, capital A2, and so on. If it falls, say, in capital A2, then this random variable is going to output the value little a2. We saw that this is an example of a simple random variable, but I claim now that any simple random variable can be represented this way. And this is really nice. I love to have points like that, right, in math, that anything with this property can be represented in this way, because that helps me prove things. When I have this property and I want to go forward and prove something else, I start up by saying, okay, let's represent it in this way. So my claim is that any simple random variable can be represented as a sum of real numbers times indicators like this. Not only that, but we can have these real numbers be distinct, and these sets will all be in F. If we do have a random variable, then we do have measurability. And those sets A will form a partition of omega. They will be disjoint, and when union together will cover the entire omega. So I know we already talked about this, but let me just say it one more time. Why are these distinct? They don't have to be distinct, but if you have points in omega that map to some A1, and a different set of points that map to A3, but A3 is the same as A1, then basically you have 2 sets mapping to 1 point. So you can union them, and you can cut down the number of sets by 1 or more. So if they're not distinct, when you have a simple random variable, you can rewrite it to make sure they are distinct. Based on what we just said, I'm going to assume they are distinct. For I going from 1 to k, I'm going to pull back each individual value, and that's how I'm going to define those sets, the capital AIs. So capital AI is going to be all the omegas in omega that mapped to the particular real number little ai. Because I am starting with the assumption that x is a simple random variable, I can use property 2 of our formal definition for a simple random variable. Go back and look at that. It says that sets like this have to be in F. So all of these AIs are in S. These sets are distinct because these real numbers were distinct. Actually, I should say these sets are non-overlapping because those real numbers are distinct. And because x is a function on omega, it's taking everything in omega somewhere. So when you pull back these little a1, little a2 through little ak, you'll get to a capital A1, capital A2 through capital AK sets back here that will cover all of omega. And again, they're distinct, so we do get a partition of omega. So starting with the assumption of just a simple random variable and saying, okay, it has to take on some number of values, and here they are, we have found the sets to build it up to write it as that indicator expression that we saw on the previous slide. So again, the point of this is any simple random variable can be written in this form. I can't say this enough, or maybe I can, maybe you've heard it too much, but for any random variable, to be measurable with respect to a sigma field means that probabilities for x are completely determinable if you know probabilities for all the sets in the sigma field. So have I drilled that enough? I don't know, I might say it again. Let's look at some examples of simple random variables. Suppose I have maybe a coin tossing experiment and I have an omega that consists of the 8 possible outcomes, heads, 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 through tails, tails, tails. So we don't actually have to have an underlying experiment, but this would be like flipping a coin 3 times. I'm going to let a random variable x be 1 if the outcome is heads, 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 or 0 otherwise. So this is a function from omega. Let's write it just a little bit differently. We get the value 1 if we plug in little omega as the point heads, 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 and we get the value 0 if we plug in any other little omega from this set. I'm going to look at a sigma field. I'm going to look at a couple of them. So I'm going to call this curly F1, and this is going to be defined as the power set on omega. So that's the set of all possible subsets. I'm going to assume that we have a probability measure defined for all possible subsets of omega for all sets in curly F1. Now, the probability that, say, x is 1 corresponds to the probability that the experiment resulted in heads, heads, heads. This is a singleton set, and I know the probability because we specifically chose a sigma field that assigns probabilities to every subset of omega. So we're trying to build up whether or not this is a measurable function, and it's looking pretty good here. You can also pull back the 0 number and realize that the probability that the function results in a 0 is just the probability you're in the rest of this space, excluding heads, 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 and that is a set in this sigma field because it contains all possible subsets. And you could consider pulling back the number 7. The set of omegas for which x maps to 7 is the empty set, and that is going to be in the power set as well, or any sigma field defined over here. Let's move to a different sigma field. I'm going to call it curly F2. I'm going to define it to have the empty set, the full omega, the singleton set, heads, heads, tails, and the rest of the space. So I just wrote heads, heads, tails complement instead of writing a set of 7 outcomes here. If we assume that P is defined for all the sets in here in this curly F2, the probability that, say, x is 1 is the probability measure of the points in omega that map to 1. And those points in omega here are just the singleton set consisting of the outcome heads, heads, heads. And I don't know what this is because I have defined a probability measure for all sets in this sigma field, and the singleton set with heads, heads, heads is not in this sigma field. So I don't have the definition of P, so I can't work with probabilities, as they relate to x. So this function here is not measurable with respect to this sigma field. Now, we looked at all possible subsets, the power set, and we looked at a very kind of restrictive sigma field here. But this begs the question, is there a maybe smallish sigma field with respect to which x is measurable? There is, and we're going to call it the sigma field generated by x. We're going to denote it with a sigma of x, and this is defined as the smallest sigma field with respect to which x is measurable. As we've seen before with other smallest sigma field statements, we can produce this sigma field by intersecting all possible sigma fields with respect to which x is measurable, because the intersection of sigma fields is always a sigma field. That doesn't mean we can do it in practice. but that is one way you might see this defined as the intersection of all sigma fields with respect to which X is measurable. For a simple random variable, I was going to say quite easy, not so easy maybe to write down, but all you need to do is pull back the individual K values, and that is not a sigma field necessarily, so you have to throw in the empty set, you have to throw in the omega, you have to throw in complements and unions, countable unions, and build it up to be a sigma field. So although you may not be able to carry this out in practice, in theory, you can find the sigma field generated by a simple random variable by just pulling back the individual points that the random variable can take on, and then starting there with that collection of sets and building up a sigma field. In other words, this random variable, the sigma field generated by this random variable, is the same as the sigma field generated by the sets capital A1 through capital AK. And we have talked about those sorts of things in the past. Okay, so I have a theorem for you. I'm going to let X be a simple random variable. Part 1 of this theorem says that the sigma field, sigma of X, consists of all subsets of omega of the form, basically what we get when we pull back any subset in R, not necessarily Borel sets, but anything. I really like this theorem for the same reason I mentioned earlier for something else. It is characterizing what sets in sigma of X look like. So maybe later we're going to have to prove that sigma of X is contained in some other sigma field. And how would you do that? In general, you would probably try to take an element from sigma of X and show it's in the other sigma field. And if I take an element in sigma of X, I can now say it looks like this. So I can say grab an element from sigma of X, and there is some subset H of R. We can write it like this, and we can now assume it has this form and go forward in the proof. The second part of this definition is that we have a probability space and an underlying sigma field, and we have a random variable X that is measurable with respect to that sigma field. And the random variable creates its own sigma field, and we can talk about a new random variable measurable with respect to the sigma field created by X. And we have a property that says a simple random variable Y is measurable with respect to the sigma field generated by the simple random variable X if and only if Y can be written as a function f of X, where f goes from R to R. Again, if we're trying to prove some bigger result and we have a random variable taken out of the sigma field generated by another random variable, we can say, oh, step 1, I know it has this form, and go forward. So this is really useful. We are going to prove this theorem. We're going to prove it at the very beginning of the next video. The reason I'm waiting is because I now want to talk about sigma fields generated by multiple random variables, and ultimately the sigma field generated by a sequence x1 out through some xn. And if we restate and then prove this theorem for this vector-valued random variable, then we will have the proof for this if we just plug in n equals 1. So I am going to hold off on the proof of this theorem until we know more about vector-valued random variables. But before we get there, let's look at an example of a sigma field generated by a simple random variable. For my first example, I'm going to take my random variable to be a simple indicator, taking the value 1 or 0, depending on whether or not little omega that it's mapping from omega falls in some set A or not in A complement. And if this is truly a random variable, then this A has to be in the sigma field F. So this is the setup. What does the sigma field or the sigma field generated by X, what does it look like? According to the previous theorem, once we've proven it, we know that we can look at any subset of R. We don't have to even worry about what is a Borel set and what's not. So any subset H and look at the inverse image. The inverse image of a subset H from the reals is going to be the set A if and only if that set H contains the value 1 and does not contain the value 0. So again, H is in the reals, and if it contains the value 1 and not the value 0, then the inverse image is going to be the set A, which is what produced the value 1. The inverse image of this set H is going to look like A complement if H contains the value 0, but does not contain the value 1. If H contains both 0 and 1, then pulling that back, everything maps to 0 or 1. So the inverse image of H is going to be the full omega. And if H does not contain either 0 or 1, then nothing maps to these points in H. And so the inverse image of that set is going to be the empty set. Okay, so we've actually covered all possibilities for what a subset H of R might look like and got 4 possible sets back in omega. This is the sigma field generated by X for this example. Let's look at the same thing, but with more values. So a more general simple random variable, because our indicator certainly was a simple random variable. I'm going to suppose that my simple random variable takes on k values, little a1 through little ak, and for reasons we discussed before, I'm going to assume that those are distinct values. Now those values, little a1 through little ak, are going to correspond to subsets of omega, capital A1 through capital AK. And I'm going to take any subset of R because I'm trying right now to characterize the sigma field generated by this random variable. So if I take a subset H of R and look at the inverse image of H under this mapping X, you'll recall that 4-point example with the picture. If my subset H of R captures exactly 1 point, it's going to map back to that corresponding set. Like little AI is going to go back to big AI. But if it captures 2 of them, little AI and little AJ, it's going to map back to the union of capital AI and capital AJ, and so on. So here I have to consider all subsets of the K points. So I can possibly get little A1 and little A3 and little A5 in my set and nothing else, and that's going to map back to a certain union of the A's. And so we can write this set as a union as I goes from 1 to K of the sets capital AI, as long as these are indexed by little ai being in H. Recall what we're trying to do here is to find the sigma field generated by X, because what we're doing looks a lot like showing the function is measurable. That pullback thing we were doing before with the 2 blobs and the 4 points, that was not about a sigma field generated by a random variable. It was about when is that random variable measurable. And so don't get confused. This looks a lot like that, what we're doing now. We are trying to find the sigma field generated by X, and we have a theorem that says, and we will prove it, that the sigma field generated by X consists of all sets of the form X inverse of H, where you run over all H subsets of R. So for any H that's a subset of R, we have a picture now of what this inverse image would look like. We're going to get a union of the sets capital AI if the little AIs, the corresponding little AIs, are in H. So do we have a sigma field? We are collecting all possible unions of all possible sizes, unions of 2 things, 3 things, 4 things, up to K things, of the sets capital A1 through capital AK. So that's what we already wrote down on the previous slide. We need for it to be a sigma field for us to throw in omega, but we don't have to throw in omega, because for a simple random variable, the sets capital A1 through capital AK form a partition of omega. They are disjoint, and when you union them, you get omega. And we have defined the collection that we're looking at as all possible unions of the AI. So certainly A1 union A2 out through union AK, which is omega, is already in there. Does it contain the empty set? So by definition, I talked about this on the previous slide, if none of the little AI are in H, then our X inverse of H is the empty set. So we already have that taken care of as well. And what about complements? Should we throw in complements? Suppose that you pull back a set, and that set that you pull back, maybe it contains the point little a1 and little a3 and none of the other points. So it pulls back to capital A1 unioned with capital A3. Do you have the complement of that set in there, or do you have to put it in? You already have it, because the complement of the union of little a1 and little a3 is the union of the rest of the capital A's. Capital A2, capital A4, out through capital AK. And that's already included, because we're starting with the collection of all possible sets, of all possible unions, of all possible sizes of the A's. And so we're finding that we actually already have the sigma field, that there's nothing we have to throw in, at least so far. We already have the omega, we already have the empty set, we already have complement, and countable unions are also already there. we don't have an infinite number of sets, so any countable union is going to be really a finite union or a repeated kind of union if you want to write a union of the same sets over and over again. But all unions of these A's are already in there. My point is that the inverse image of any subset H of R looks like a union of some of the AIs. And those capital AIs are determined by whether or not the little AIs are in H. And to fill this out, to make it a sigma field, there's nothing more to do. We've got it. The sigma field generated by X consists of the union of the AIs, where the I's here are unioned over an index set that I'm going to call capital I. And capital I is some subset of the numbers 1 through K. So it could be all 1 through K. It could be the subset 3 and 7 and 8. We're going to hit all possible unions this way. And if and the empty set is also allowed for I. So that's how you would get an empty set over here. And if your subset I of this was the entire set, that's how you get the omega over here. And indeed, this sort of description describes everything in a sigma field generated by this random variable, a simple random variable in this form. Now I claim this is the same as the sigma field generated by the sets capital A1 through capital AK. And to show this, note that any set in here can be constructed from these sets, and any set in here is in here. Because, for example, if you look at capital A3 over here, that consists of the union over here, where the index set is just the singleton set 3. So the generating sets are equivalent. So the sigma fields are equivalent. And so from now on, when we look at a simple random variable, we'll say, we proved today that means it has this form with these little AIs and these capital AIs, and the sigma field generated by that simple random variable is equivalent to the sigma field generated by the capital AIs. Let's look at one more kind of silly example, and that is a constant random variable. Random variables don't have to be random. You can have a random variable that's equal to 3 no matter what. I'm going to toss that coin and assign X to be 3 no matter what. So it's constant, but in a probability, we say that it's constant with probability 1. So this means that I've got like an X of omega that is some C for all omega in capital Omega. This is how we define a constant random variable taking on the constant value C. For any H subset of R, this is how we characterize the sigma field generated by X. When we pull back, we either get the full omega or we get the empty set. So we're going to get the full omega if the subset H in R contains the value C, and we're going to get the empty set if it doesn't. And so putting these together, we have a valid sigma field. There's nothing else that needs to be thrown in. It is the so-called trivial sigma field consisting of the empty set and omega, and this is the sigma field generated by a constant random variable. Wow. So future me here in editing, I just noticed how long this video is getting. I try to keep these videos between 20 and 25 minutes, and we're already over 30 minutes. So I'm going to stop it here, and anything I might have said in this video that we are going to do today, we're definitely going to do in the next video. And you probably won't have to wait too long for that because it's already been recorded and partially edited. So I hope to see you there.